Bismillahirrahmanirrahim. Let's start our next lecture. Our next lecture is on chapter number 13 of our book Fundamentals of Heat and Mass Transfer by Incorporeal and Dewitt, and the title of this chapter is Radiation Exchange Between Surfaces. So over here we would be talking about the heat transfer between two or more surfaces. In fact, we will go up to 3 surface enclosures. Chapter 12 was about the physics of radiation, the radiation processes and properties and related properties. So that information will be used in this chapter. These are some of the topics that we would be covering in this chapter, inshallah ta'ala. We would be covering the topic of view factor or shape factor, and then radiation heat transfer between black surfaces, radiation heat transfer from a gray surface, net radiation heat transfer to or from a surface. And while discussing net radiation heat transfer to or from a surface, we will come across this concept of surface resistance. And then next topic would be net radiation heat transfer between two surfaces. And while going over this particular topic, we will come across the concept of space resistance, and then we will extend this radiation heat transfer topic to 3 surface enclosures, where we will be solving the problems using thermal radiation thermal network. So it is a very interesting chapter. Let's start this thing. In fact, we are going to start the view factor. First of all, we need to understand why do we need to learn the view factor. See, if there are certain walls in this room, and let's say if this is surface 1 and say this is surface number 2, and we are interested, means the floor is surface 2, and if we are interested in finding out the heat transfer due to radiation between surfaces 1 and 2, so then it cannot simply be sigma epsilon A T14 minus T2 raised to the power 4. Rather, we need to take into account the fraction of the radiation which leaves 1 and is being incident upon 2. What is the reason? Because the radiation which is leaving surface 1 is not only incident upon 2. Some of that radiation would be incident upon 2, but some of that radiation which is leaving 1 is in fact going on other surfaces, such as this window. Some of the radiation which is leaving 1 is being incident upon the roof and other walls, for example on the front wall and other walls, so and other objects as well. So all the radiation which is leaving 1 is not being incident upon 2. So what we need to do is that we need to find out that fraction of radiation which is leaving 1 and is being incident upon 2, which is directly striking surface 2, because that is that fraction of radiation, or that is that portion of radiation, rather fraction, which would be responsible for radiation heat exchange between 1 and 2. The other part of the radiation which is leaving 1 and is not being incident upon 2, which is going, for example, on this window or on the roof or on other walls, that has nothing to do with the radiation heat transfer between the surfaces 1 and 2. So that is why we need to find out that fraction which is leaving 1 and is being incident upon 2 directly, and that is found out with the help of a parameter which we call view factor. So radiation heat transfer between the surfaces depends upon the orientation of the surfaces relative to each other, as well as their radiation properties and temperatures. Of course, we know that the higher the temperature of the body, it will emit more radiations, and the radiation heat transfer will depend upon the emissivity of the surface, absorptivity of the surface, reflectivity of the surface, etc., etc. But along with all those, the radiation heat transfer mainly depends on the orientation of the two surfaces. So that orientation aspect is found out using the view factor. It takes into account the effects of orientation on radiation heat transfer between the two surfaces. It is a purely geometric quantity. Right? So it is denoted by Fij, where Fij would represent the fraction of the radiation leaving surface I that strikes surface J directly. So if we talk about the previous example that we were discussing over here, and if we want to find out radiation heat transfer between surfaces 1 and 2, so we would be finding out F12. F12 would mean the fraction of radiation which is leaving surface 1 and is striking surface 2 directly, because that is that portion of radiation which is responsible for radiation heat transfer between the two surfaces. So we need to find that out. Let's take a look at some of the view factors, some of the values of the view factors. See, if we have got a plane surface, right? So in this case F121 would be 0, because the radiation will not be incident upon itself in this manner. It will not get bent and it will be incident back onto itself. Now this is not going to happen. So in this case F1 onto 1 is 0, means the radiation leaving 1 and is being incident upon 1 does not exist. Again, that does not mean that F121 will always be 0 no matter what. It would in fact depend upon the geometry. For example, take a look over here. If this is 3, now over here there is some radiation which is leaving 3 and is being incident upon itself. So in this case F33 will not be 0. So it would depend upon the geometry of the object. So again, it does not mean that in the curved surface F from that surface onto itself would always be non-zero. No, even in the curved surface it may be 0. For example, over here, see, if we talk about the radiation leaving the other side, the other side of the curved surface, so in this case the radiations will not get bent onto itself. The radiations will not get bent onto the surface itself. So in this case F22 will be 0, right? So this is just to give you a little bit idea about some values of the view factors. We would be discussing view factor in much details, and we would be finding view factors for certain geometries. Now we will go over 4 view factor relations. The first one is called the reciprocity relation, and the reciprocity relation is written in this form between any two surfaces. In general, we may write it as AIFIJ is equal to AJFJI, or A1F12 is A2F21, or A3F34 is A4F43. So it can be written in this form between any two surfaces. So with the help of the reciprocity relation, we can find out the other shape factor or view factor, provided we know one of the shape factors, because the areas would in fact be known. The second one is summation rule. The summation rule says that Fij is equal to 1, or F11 plus F12 plus F13 and so on is 1. Now what does this summation rule mean? It means that if, let's say, if this wall is surface 1, so from this wall the radiations would get emitted, would leave this surface, and they will be incident on let's say this wall, you may call it 2, and the radiations leaving 1 will also be incident upon this side wall. We may call this wall as 3, as surface 3. Radiation leaving one will also be incident upon this floor, and we may call the floor as 4. The radiation leaving one will also be incident upon the rooftop, and we may call the rooftop as surface 5. And there would be one wall which would be exactly opposite to 1, right? Which would be exactly opposite to 1, which would be adjacent to 3 and 2, just opposite to 1. So radiation leaving 1, where is the radiation leaving 1 going? It is leaving 1 and is being incident upon 2, it is being incident upon 3, it is being incident upon 4, it is being incident upon 5, and it is also being incident upon 6. So if we add up all those fractions, what do we get? 1 or 100%. So this is what summation rule is all about. The third relation is called the superposition rule. Superposition rule is a very simple rule and it is very logical. It says that f from fraction of radiation leaving 1 onto 2 and 3 combined. Right? If this is 2 and if this is 3. So that would be equal to fraction leaving 1 and which is being incident upon 2 plus fraction of radiation which is leaving 1 and that is being incident upon 3. So that's quite logical, but what is the use of this superposition rule is that sometimes we would not be able to find out the values of f using the tools that are provided. We will be provided with some tools such as some expressions, some formulae, some charts, some figures. So sometimes it would happen that we would not be able to find out the value of f using all those tools. So we would be able to, if we can somehow find out any two of those three using those tools, then we can apply the superposition rule to find out the third one which cannot be directly found out using those tools. So that is the advantage of superposition rule. The last is the symmetry rule. So for example, you can see over here that F12 would be equal to F13, because 2 and 3, as long as 2 and 3 are having the same area. Similarly, F14 would be equal to F15 if the floor area and the roof area are the same. So with the help of the symmetry of the objects, we can apply the symmetry rule and say that if F12 has a particular value, then F13 would have the same value, as long as the objects are symmetric. Now in this table 13-1 of our book, we are given several geometries and then we are given the relations for Fij, where this is surface I and this is surface J. So there aren't only two geometries, rather it is a long list. So you can take a look over there. Let's take this problem so that we can get acquainted with the use of the shape factors. It says it's 13-1 of our book, and it says determine F12 and F21 for the following configurations. And we are given like 4 or 5 parts in this problem, but we would be covering only a couple. For the following configurations using the reciprocity theorem and other basic shape factor relations, and we are being asked not to use any tables or charts. So we have to use those 4 relations of a view factor, and we are not allowed to refer to any tables or charts that we will look at in a bit. So now in this case we need to find out F12 and F21. So if you take a look over here, what is this geometry? What is this figure? It is a pipe, and it is not a complete pipe, rather this is like 75% of the pipe, 3/4 of the pipe. And over here we have got two surfaces which would of course be rectangular, such that this such that this angle is 90 degrees. Now uh, in this case there would be four shape factors. Primarily looking at it, there would be four shape factors: f11, f12, f21, f22. So if we can find out readily some of the shape factors, that would be very handy. So we can see that since, by the way, you need to focus upon those shaded areas. So since this side is shaded, since this side of A1 is shaded, it means that the radiation heat transfer is not being considered on this side. Rather, it is being considered on this side. So radiation leaving 1 will, where would it go? Of course, it will not get bent and it will not be incident upon itself. So where will it go? Where will it go? The radiation leaving 1 will only be incident upon 2. So since we have just said that the radiation leaving 1 will not get bent and it will not be incident upon itself, so therefore F11 would be 0, right? F11 would be 0, and F11 plus F12 is equal to 1, which is the summation rule. But whenever you apply the summation rule, kindly take a look at it whether you have written it correctly or not. See, what does this sentence mean? It means that the radiation leaving 1, which is being incident upon 1, and plus means and the fraction of radiation which is leaving 1 and is being incident upon 2 is all the radiation, is 1 is 100% of the radiation leaving 1. Is it this way? Is all the radiation leaving 1 being incident upon 1 and 2? Of course it is, out of which we know that F11 is 0. So all the radiation leaving 1 is being incident upon 2. So therefore, using this equation, we can then write that F2 is 1. F12 is equal to 1 means the radiation leaving 1, which is striking surface 2 directly, is 100%. Means radiation which is leaving 1 and is being incident upon 2 is all the radiation, and the radiation leaving 1 is not going at any other surface. Radiation leaving 1 is not going at any other surface besides 2. So we have found out F12. Now if after finding out F12, we can very easily find out F21 using reciprocity, right? But of course we can write this expression F21 plus F22 is equal to 1, but F11 was 0. Similarly, is F22 0 as well? F11 was 0, is F22 0 as well? See, where is radiation leaving 2 going? Radiation leaving surface 2 is being incident upon 1, right? It is being incident upon 1. Is it being incident at any other surface? Radiation leaving 2 is being incident upon itself as well, right? So over here F22 is not 0. However, F11 was 0, as I just mentioned earlier that it depends upon the geometry. So in this case F22 is not equal to 0. So we cannot just write F21 as equal to 1. So once we have found out F12, finding out its counterpart such as F21 is not a problem at all, because we would be knowing the areas. So if we apply the reciprocity, we will write it in this form: A1 F12 is equal to A2 F21. Now what is A1? The area of these two plates. These two plates make A1. So what is the length of these two plates? This length is the length of this side is the radius of this circle, means you can say R, times the length of this pipe, and you may take the length of the pipe as L. However, we are not given any information, so you may take the length of the pipe as L. So the area of this plate, right, area of this plate would be R times L, and there are two such plates. So the total area of A1 would be 2 times R into L. F12 has already been found as 1. A2. Now A2 is is this circular object, but it is not complete. Rather, it is 75% of the total circular pipe. So the total area of the circular pipe would be pi dl, and we have got how much? 75% of it. So you can multiply this pi dl by 0.75 or 3 by 4. It's the same thing. Times F21, which is the unknown. This is the unknown. So this 2r will get cancelled out, because 2r would become diameter, and this length will also get cancelled out. So we will be left with 4 upon 3 pi. We will be left with 4 upon 3 pi means 0.424. Now this 0.424 means that 42.4% of the radiation leaving 2 will be incident upon 1. 42.4% of the fraction, 42.4% of the radiation leaving 2 will be incident upon 1. And where will the rest go? Where will like 57.6% go? That would be the value of F22. That would be the value of F22. Means 57.6% of the radiation leaving 2 is being incident upon itself because of the geometry. And 42.4% of the radiation leaving 2 is being incident upon 1. Let's take part B as well. Again, the problem is the same. We have to find out F12 and F21. And in this case, we are given a small sphere of area A1 under a concentric hemisphere of area A2. So we have got this small sphere having an area of A1 placed under a concentric means they both have got the same centers. Concentric hemisphere means this A2 is not the complete sphere, rather it is half the sphere only, such that A2 is equal to twice of A1. So is F11 0? Again, there would be 4 as you can say shape factors: F11, F12, F21 and F22. So can we say anything about F11? See over here, the inner portion of 1 is shaded, so it means that we will not be considering radiation heat transfer from the inner side of A1. So we would be considering radiation heat transfer or the radiation leaving 1 from the outer surface. So if we consider it from the outer surface, so the radiation leaving 1 will be going in this direction, for example, right, in this direction, and it will not get bent back onto itself. So therefore F11 would be 0. However, if the outer portion of 1 had been shaded, so what would that had meant? It would have meant that we need to consider the radiation from the inner surface of 1, and in that case F11 wouldn't had been 0. Okay, so can we, so after finding out that F11 is 0, is F22 0 as well? Of course you would have found out that F22 is not 0. There would be radiation leaving 1 and which would be incident upon itself. So F22 will not be 0. So can we then write F11 plus F12 as 1 using the summation rule? Can we write F11 plus F2 is equal to 1 using the summation rule? In fact, we cannot. See, I had told you in the previous part that whenever you write this statement, you need to assess whether this is actually what is happening. What does it mean? It means that the fraction of radiation leaving 1 which is being incident upon 1, which is 0, plus the fraction of radiation leaving 1 and is being incident upon 2, if we write is equal to, so that would mean that that is all the radiation. Is it true? Is radiation which is leaving 1 is only being incident upon 2? The answer is no, right? How? Because there is some radiation which is leaving 1 and this radiation is not being incident upon 2. So this statement is therefore, the summation of these two terms will not be equal to 1. So what we need to do over here? See, we need to assume another surface over here, and we will then call it 3. We will then call it 3, and then we would then write f11 plus f12 plus f13 is equal to 1. f11 plus f12 plus f13 is equal to 1. Assess this statement as well. Is it true? It says radiation leaving 1 and is being incident upon itself, which is 0 of course, plus radiation leaving 1 and is being incident upon 2, right? Radiation leaving 1 and is being incident upon 2, right? Plus radiation leaving 1 and which is being incident upon 3, which is being incident upon 3, is 1 or 100% of the radiation leaving 1. Now this is true. This is true because the radiation leaving 1 is only going on 2 and 3. Radiation leaving 1 is only going on the upper hemisphere and the lower hemisphere, means it is going on 2 and 3 and nowhere else. So f12 plus f13 is 100% or 1. Now similarly f21 plus f22 plus f23 is equal to 1. Is it true? f22, f21, f21, what would f21 be? f21 would be the radiation which is leaving 2 and is being incident upon 1. So f21 will have a particular value, it will not be 0. Plus f22, of course it will also have a particular value. Is it all the radiation leaving 2? The answer is a clear no. There is some radiation which is leaving 2 and it is not being incident upon either 1 or 2. Rather it will be incident upon the lower hemisphere, which was not given in the problem. Means it will be incident upon 3. So therefore f21 plus f22 plus f23 would be the total radiation leaving 2, would be the total radiation leaving surface 2. And by symmetry you can write this statement. By symmetry you can write that f12 is equal to f13. Is it true? Because you can see that the half of the radiation leaving 1 will be incident upon the upper hemisphere and half of the radiation leaving 1 would be incident upon the lower hemisphere. So we have used the symmetry rule as well over here, right? Now since we have found out f12, finding out f21 should not be a problem at all. And once we have found out f12, we will find out f21 using reciprocity. And it says a1 f12 is a2 f21. See, a2 over a1 is 2. We are given this statement, right? We are given this relation between a1 and a2. And we have found out the value of f12 as 0.5. So putting the values, we get f21 as 25%. It means that 25% of the radiation leaving 2 will be incident upon 1. 25% of the radiation leaving 2 will be incident upon 1. Where will the rest 75% go? It will be incident upon itself and it will be incident upon 3. Means f22 plus f23. Means f22 plus f23 would be 0.75, 75%. Would f22 and f23 would be the same? Would f22 and f23 be the same? Would it be 0.75 by 2 each? Would it be 0.375 each? The answer is no, because they are not symmetric, right? Okay, now we are going to discuss table 13-2 of our book. Table 13-2 has got 3 geometries. One aligned parallel rectangles, in which you can see that there are 2 rectangular surfaces I and J. I and J. And those 2 surfaces are L distance apart, where the dimensions of that surface are x and y. And if this is so, we can find out Fij using this long expression. So it may be, for example, a rectangular furnace, and if we are interested in finding out the heat transfer between the floor of that furnace and the roof of that furnace, and we know the dimensions of the floor and the roof and the distance between the floor and the roof, then we can use this long expression to find out Fij. Kindly note that this expression will give us Fi to j from the floor to the roof, and if we want to find out Fji, we can always use reciprocity or any other theorem such as symmetry if it is applicable. Now the second case is that of the coaxial parallel disk. This second case is almost the same as the first case, with the difference that over here the surfaces are no more rectangular, rather they are circular, and the radius of this surface is Ri and the radius of this surface is Rj, and again they are L distance apart. So if the furnace is circular, we can find out Fij using this expression, where S is this, can be evaluated using this expression, and Ij, Ri and Rj are given over here. The last case, the third case after parallel rectangles and after parallel discs, coaxial parallel discs, is that of a perpendicular rectangles such that those perpendicular rectangles share a common edge. It is important that they must share a common edge. So if this surface is I and the vertical surface is j, and the dimensions of the floor, for example, are x and y, and the height of the vertical surface is z, so we can then use this very long expression to find out the value of Fij, fraction of the radiation leaving surface I, which would be incident upon surface j. Now in fact, if we want to find out Fij for any of those three cases, the good thing is that we do not need to use those very long expressions. Rather, those very long expressions have been converted into some easy to use charts. See, this chart corresponds to the first case, aligned parallel rectangles. All we need to do is calculate x by L, where x is this length and L is the distance between the two surfaces, and calculate y by L, where y is this length and L is the distance between the two surfaces, and at the intersection of the two values we will read out the value of Fij. So it would be Fij from I to j. If we want to find out Fji, we can then make use of reciprocity or any other theorem. You can see that the maximum value of f goes up till 1 because it cannot exceed 100%. The second case, this chart pertains to the second case of coaxial parallel discs. So over here we need to calculate two parameters again. One is L over Ri, where L is the distance between the two discs and Ri is the radius of this surface, and Rj over L, where Rj is the radius of this surface and L is the distance between those two surfaces. So if we calculate L over Ri and Rj over L, we would be at the intersection of the two, we would be able to read out the value of Fij. And this one is for the last third case, where the two surfaces are perpendicular and they share a common edge. So in this case again we need to calculate two parameters. One is z by x and the other one is y by x, and at the intersection of these two we would be able to read out the value of Fij. So we do not need to use those lengthy expressions, rather we can use those very easy to use charts to find out the value of Fij for those particular geometries. Now let's take problem 13-9 which says consider the perpendicular rectangles as shown. Determine, and we have to determine the shape factor F12. We have to determine the shape factor F12. So we have to determine the shape factor F12. So which case would it be? It would not be the first case because they are not parallel rectangles. It would not even be the second case because these two surfaces 1 and 2 are not discs. However, it may be the third case because the two surfaces 1 and 2 are perpendicular to each other. But those two surfaces 1 and 2 do not share a common edge. They do not share a common edge. So what we need to do over here is that we need to come up with the surfaces such that we make them share a common edge. Such that we make them share a common edge. So that we can make use of that chart. So that we can make use of this diagram, of this chart. Unless if the two surfaces are rectangular but they are not sharing a common edge, then we would not be able to use this particular diagram to read out the value of Fij. Now the thing is, the question is how we can make the surfaces share a common edge. How we can make the surfaces share a common edge. Of course 1 and 2 will not be able to share the common edge because they have this grayish surface in between the two. So 1 and 2 will never share a common edge. However, what we can do is introduce a new surface over here. And call it 3. We can call this grayish surface as 3. So what is the advantage of introducing this surface? See, what can you say about 2 and 3 now? Are 2 and 3 perpendicular to each other? Yes, they are. Do they share a common edge? Yes, now 2 and 3 they do share a common edge. So are 2 and 3 only surfaces that share a common edge? Are these two surfaces the only surfaces that are sharing a common edge? The answer is no. How? Because 2 and 3 when combined, 2 and 3 when combined are perpendicular to each other and they are sharing a common edge. So what F can we find out using that chart? Can we find out F21? No, we cannot find out F21 directly from that chart because 1 and 2 are perpendicular but they are not sharing a common edge. Can we find out F23? Yes, we can find out F23 because 2 and 3 are perpendicular and they are sharing a common edge. Can we find out F2 to 3 and 1 combined? Can we find out F from 2 on to 3 and 1 combined? Yes, we can, because 2 and 3 when combined are perpendicular to each other and they are sharing a common edge as well, right? So how we would proceed? See, we can use this expression. We can start with this expression. F from 2 on to 3 and 1 combined would be equal to F2 to 3 plus F2 to 1, right? This simple logical expression is what we know as the superposition rule. Now you will see the advantage of superposition rule. See, out of these 3 F's, can we find out F21 using that chart? The answer is no, because F21, 2 and 1 surfaces are of course perpendicular to each other but they are not sharing a common edge. Can we find out F23 from that chart? Can we find out F23 from that chart? Yes, we can, because these two surfaces are perpendicular to each other and they are sharing a common edge. Can we find out F2 onto 3 and 1 combined using that chart? Can we find out F from 2 onto 3 and 1 combined from that chart? Yes, because 2 and 3 and 1 combined are perpendicular surfaces and they are sharing a common edge. So we would be able to find out these two using that chart. And with the difference of these two, we will be able to find out F21. And once we find out F21 using reciprocity, we will then be able to find out F12. So this is how we will proceed with the problem. Now, in order to find out F23, see, what do we need to calculate in order to use this chart? We need to calculate Z by X and Y by X. We need to calculate Z by X and Y by X. So what is Z by X? Z by X in case of F23. In the case of F23, Z would be the height of 3, which would be 0.2, and X would be this length, which is given as 0.5. So Z by X would be 0.2 over 0.5 means 0.4, and Y by X would be 0.3 over 0.5 means 0.6. Kindly note that it does not matter what is X and what is Y in the diagram. What matters is that what is X and what is Y in this particular diagram, because we will go with this X, this Y and this Z. not the ones that are given in the problem if they are any different from these notations. So at the intersection of 0.4 and 0.6, going back, at the intersection of 0.4 and 0.6, so we will get a value slightly less than 0.2. So we can take this f as 0.19, and what it would be? It would be Fij. It would be Fij. So what is our I? Our I is 2 and our j is 3. Our I is 2 and our j is 3. So F23 would be 0.9 or 19%. Now it means that 19% of the radiation leaving 2 is being incident upon 3. 19% of the radiation leaving 2 is being incident upon 3. But based upon this knowledge, we cannot say that F21 would be 81%. We cannot say that F21 would be 81%. Why? Because the radiation leaving 2 would be incident upon 3. Radiation leaving 2 would be incident upon 1. And radiation leaving 2 would go here and there as well. Here and there as well. And that is neither 1 nor 3. Right? So after finding out F23 as 0.19, we cannot write as F21 as 0.81. Because F21 plus F23 is not equal to 1. Because F21 plus F23 is not equal to 1 or 100%. There are other surfaces around which would be receiving the radiations that are leaving 2. Now for the next one, F2 onto 3 and 1 combined. What would be Z by X? Z by X for this combined surface would be 0.4, X would remain 0.5 and Y by X would remain 0.6. So now at intersection of 0.8 and 0.6, at the intersection of 0.8 and 0.6, we read the value of Fij as 0.25. It is in the middle. It is midway between 0.2 and 0.3, so it would be 0.25. So F from 2 onto 3 and 1 combined would be 0.25. So if we put those two values in equation 1, we get F21 as 0.06. Now using reciprocity, we know the areas of A1 and A2. We will get the value of F12 as 9%, as 0.9%. It means that 9% of the radiation leaving 1 will be incident upon 2. Do you think that F13 would have any value? F13 won't have any value. Right? So radiations would leave 1 and they will be incident upon 2, and they would leave 1 and they would be incident upon other surfaces which are not numbered over here. So the value of F12 that we will get out of here is 0.09, means 9%. Now let's take one more very small topic before we start the heat transfer section. It is about the view factor and this particular method is called the cross strings method. Now in the cross string methods, string means, we all know what strings mean. So over here there are two surfaces. This surface is 1, this surface is 1, and they are not having any particular shape, and this is surface 2. And if we want to find out Fij or F12 or F21 or whatever, so the Hottel's, its name is Hottel's cross strings method, Hottels, Hottel's cross string method. The Hottel's cross string method says that Fij would be equal to summation of cross strings minus summation of uncrossed strings. Cross string means those diagonal strings, those are crossed strings. Minus summation of uncrossed string means those strings which are not crossed and they are not on either side. For example, N1 and L2 are also not crossed, but they are on surfaces 1 and surfaces 2. So they will not be considered as uncrossed strings. Over 2 times string on surface I. Now for example, if you want to find out F12, so F12 would be summation of cross strings, means L5 plus L6, where L5 would be the length of this string and L6 would be the length of that string, minus summation of uncrossed strings. Summation of uncrossed strings would mean L3 and L4. They would mean L3 and L4 over 2 times string on surface I. If you want to find out F12, so I would be 1. So what is the length of the string on surface I? It is L1. So it would be twice of L1. If you want to find out F21, so The rest of the things would remain the same, only the denominator will change. It would become 2 times L2. So this is the Hottel's cross-string method, which is used for u factors between infinitely long surfaces and which do not have a very particular shape.